Suppose we're ready to go then?
Yes, please take it away.
Right up. I'm going to turn off my video here. It's a little, got two monitors going on, a little confusing. Here we go. And just sharing my screen now. Tired screen. Righto. All right, y'all seen my screen? Yeah, I can't see you guys, so give me a shout. Yeah, you can see the screen?
Yeah.
Yes.
Righto. All right, let's get started. All right, so here today, I'm Julian Kimmer. There's a GitHub link there. We're here talking about PipelineC today, and let's get into it. So first off, thanks for having me back at a Whirlwind Go at a first CIRCT talk about a year ago, actually, from now. I'd thrown together some high-level bullet points, and we had some nice discussion, but I have a more formal presentation for you guys today. So talking about that, I'm going to give you what is PipelineC, a little bit of an origin story. Is it some kind of HLS or not? Go through some fundamental building blocks, pure functions as combinatorial logic, combinatorial logic being auto-pipelined, functions with explicit or implicit state, deriving state machines, some neat stuff with wires and clock crossings. And then I want to give some time for a full example design and go through, break down the code, what it was like to debug, and show a hardware demo, talk about the results. And then, of course, some time for questions at the end. And then I have a section on explicitly how does this map to CIRCT. So, and yeah, I'm not covered. There's advanced features of the language that aren't going to be talked about here, and not necessarily talking about how it's doing what it's doing, more so what it's doing right now. So, yeah, starting with this quote here, we do these things not because they are easy, but because we thought they would be easy. Right, some internet programming meme was pretty much my thinking around 2014, 2015, because I started PipelineC not trying to be an HLS tool or even a full hardware description language, but just it seems like it wouldn't be too hard to just write a pure C function and have that, render Vhdl and have it be auto pipelined. So I thought, so I was working in that regard from 2014, 2015, and just 2016, 2017. And I brought it up to my old professor, Dr. Taskin, and I said, hey, I've been working on this tool. It can auto pipeline C functions. And he said, that's nice. Can it do anything else? Like, okay, all right. He's like, can it make a state machine? And it's like, well, no. And it's like, well, that's a large part of hardware design. So it's like, okay. So then from those years on, it was kind of like, all right, let's build on top of being able to auto pipeline a pure function and just, build out pretty much a full hardware description language based on C. So going through these bullet points here, PipelineC is more about what's inside the module, writing state machines, pipelines, inferring your block grams and your multipliers. I wasn't necessarily in love with C, but I'm an FPGA engineer for my day job, and my FPGA engineer colleagues and friends all know C. I was in a position where I was being given C code and being told, implement this on the FPGA, often involving pipelining and depipelining things quite a bit, and make that classic mistake of, adding a register here or there and not timing everything right in the surrounding modules. And it's a mess. And I, was just looking for something better, really. And how hard could it be? But to say PipelineC is less about, on the right-hand side there, stitching things together. There's a lot of great high-level tools, name some of LightX, FuseSock, silicon compilers coming in there for kind of being able to stitch a lot of different IP from a lot of different languages together in kind of a build flow package manager-ish kind of sense. And yeah, I think there's a great future in that. It's just not necessarily what PipelineC is focusing on. To that regard, like things like building a system on chip, like with a click and a few generators, it's not doing that. It's not managing like your CPU's bus and address space. It's not doing full bit stream generation for you. But and my final note I wanted to touch on there is in the bottom right that I think there is a future for block diagrams. Especially in the sense that, there's a reason why each FPGA manufacturer has a block diagram tool There are certain designs where it is a handful of blocks, wired together, and it really can be the easiest way to do it is in a GUI dragging wires. I'm not saying that's the case for all things, but for a lot of things that are not necessarily the left-hand side here, where you're describing like, clock cycles and multipliers and RAMs and state machines, but just high-level blocks linked together. I think something like a GNU Radio Companion GUI thing where you're dragging around blocks is a future where that can be going. Righto. So that's what PipelineC is about. Let's get into what are the building blocks that you're actually writing here. I mentioned it all starts with pure functions and combinatorial logic. Hardware description languages know this. Verilog and Vhdl both have a literal function you can write, and it'll give you combinatorial logic. PipelineC is sort of mixing functions and modules here from HDL. In the example here, very basic C function signature with your return type and your input types, and a name for the function. And you're going to get exactly that VHDL on the right there. And down there at the bottom, if you give it a pragma main and saying that's like saying this is a top level function, and these inputs and outputs you have, they're actually top level ports, like on the top level of your design, going out to like off chip and such. Final note there is that this combinatorial logic, whatever's in this function, this blob, this cloud here on the bottom left, all PipelineC really needs to know about it eventually is the delay through that combinatorial logic. And we'll get more on what it's doing with that later. So we got this combinatorial logic. And now, like I mentioned, the start of PipelineC is auto pipelining. It's a core feature. So what can you do? You can write a basic C function like you have on the left there, my function. And it has three inputs, the two values, and a select. And based on the select, you're going to multiply them or you're going to add them. And what PipelineC is doing for you is you write a function signature like that, and you give it what FPGA part you're working with and target frequency up there at the top, the two pragmas. And it could come up with something like in the blue there. They say, this floating point add is longer than your multiply. It's going to take 5 cycles. Your multiply is going to be split up into 3. And your select input bit is going to be delayed along through all of that, and it all comes together in the last stage there for a mux to determine your return value. And I want to note up at the top there that HLS tools can do this. You can get a Vivado HLS to do this, I know. You can give it a pragma initialization II equals 1, and it'll do this kind of thing. But it also does a lot more, maybe things you might not want either with, if it'll detect it's not II equal 1 in some cases with feedback, and it'll derive a state machine, and it'll infer RAMs, and that array argument, that's an AXI bus. Like there's complicated things that PipelineC isn't doing. It's sticking pretty simple in that regard. Righto. So this is where it gets into my professor saying, well, okay, it can auto pipeline. What else can it do? Well, by sort of abusing the static keyword of C, that actually makes sense here. You can have, a function that you're imagining being repeated. I don't know, you could say it feels some kind of like an interrupt maybe, some kind of like kernel in a GPU or something that's just over and over again executing, but these are just clock cycle level repetitions here. And it works like processes in VHDL and Verilog. So in the examples here in green there, you're declaring your variable as static. That means it's going to be a register. And then you just go at writing C code. On the left there, it increments that static variable directly and returns it. So you get all the combinatorial logic just going right out immediately. But on the right there, in blue, there's a temporary kind of RV return value variable there where you don't end up incrementing that value. It's the pre-increment value that goes right out the port, and you still end up incrementing your register value, and it gets saved around for the next cycle. And so in this way, you can have input registers, output registers, combinatorial logic in between those, anything you want. It's just a matter of declare what's a register and do combinatorial logic around it. Righto. Next bit of in red there, experimental new stuff for PipelineC here is a bit of stuff that the language Silis also does. I don't know if they've come and given a talk, but they absolutely should. It lets you do cool things like in green here, this clock function operator thing. What it's doing is when you see one of these in a function, it's saying that this isn't combinatorial logic like on the left, and it's not using static variables like on the last slide. You're doing something different, and in this case, it's deriving a state machine for you. So on the left there, like I said, there's none of that clock stuff, just combinatorial logic. And in the middle here, you have a clock before the increment of your return value, but on the right here, you have the clock after the increment of your return value. And depending on the placement of that clock, you get different implicitly derived registers. In the middle case, you need to save the X value in a register, where on the right case, you're saving the return value result of the addition in a register, and that goes out in the next state. The final thing I'm wanting to notice here is that it's saying like this is the first state and then the second state, before that clock and after that clock. But these functions are occurring like they would be called from another function. So there's actually a state where you're entering this state machine function, then you go through your first state, second state, and there's actually a state after where you're returning from this state machine function. And that's all done with handshaking, so you can get a series of nested state machines and execution structured like that. That's probably about all I'll say regarding this kind of experimental new derived state machine stuff here, though it is neat. It's not actually talked about a lot for the rest of the talk here. Getting on to something, that is definitely used in the demo coming up. So you can have multiple of these functions that were main. So in this case, there's a function A and a function B. They exist separately. They are both top-level functions. They could both have top-level I/O. But in this case, we're demoing something called global wires, or you can get into clock crossings this way. So you have this thing at the top here, this the wire declared in the global namespace outside of either of these functions. And using these wire write and wire read macros here, what it's doing in hardware is literally connecting a wire out from one of the functions across and into the other, writing in one, out, reading into the other. And this is just really useful functionality. So in this case, it's both the same clock domain on both sides here in the A function and B function. So it is just a wire. You can string a wire between these two domains, but it is aware of, say, if function B was at 200 megahertz, it would now provide you not an interface of a wire. You would get errors and things if you tried to use a wire, but an interface for a deserializer for those, that 2x faster domain. And if you don't have synchronous domains, you can get it to infer FIFOs, asynchronous FIFOs. You could say this wire is asynchronous, ignore whatever it's doing between these two domains. It's always going to be a wire. Per that last slide, when you're deriving state machines, there's been some really neat work using these wires to wire together global resources and kind of share things between state machines over time. That last bit of line down there, I mentioned PipelineC is not about kind of high-level stitching of blocks together, but you can absolutely do that with this, and I've had good success doing it, where you have blocks or multiple blocks that have an interface exposed in the global namespace, and that's kind of what other blocks are expecting to wire up to. So just kind of pound include into your file, a bunch of your main functions and all the logic they do and the wires they expose, and bring in another chunk of code and start using it right away. It's pretty useful. Generally good for just wires that you're going all over the place that you don't want to have to, manually wire through each hierarchy boundary, resets. And it's good for debug switches. You want to quick debug and send a switch down into that module, or send a value up to an LED for debug. Like, don't bother, sending it through all your levels of hierarchy. Just read wire, write wire kind of deal. All right.
Sorry, are you taking questions over the course or saving them to the end?
Happy to take a question, but I did definitely allocate some time there at the end. But go for it. Yeah, what do you got?
Really, you can talk more about this during question session, or maybe not at all, and I'll ping you offline. How does this work? How do you do in particular, how do you do the arbitration? Just, like 5 seconds, 10 seconds, and then we can talk more about it later.
Right. So in the everything that's not the arbitration between derived state machines, that's a little fancier. And I think I touched on that a little on the next slide or so. But the stuff above it, that's like wires, deserializers, FIFOs, that being for a wire, you can't have multiple drivers. So you'll get an error if you try to write wire on a wire multiple places. But you can read that wire in multiple places just fine. I don't believe the multiple read side is set up for like the deserializers and FIFOs, but that's the sort of checking that's going on. Like you can't have multiple drivers, so there isn't an arbitration there. You just can't do it other than the fancier actually inferred arbitration stuff that happens. Is that sort of clear? So it's kind of delicate in its use. You can't just go reading and writing however you want, but there is checking there to help you out.
Yeah, that's good to know. I am particularly interested in how you're doing, like how you're arbitrating. But again, I'll just ping you offline. We'll talk about it.
Sounds good. Yeah, you'll have some more here too. Let's see. Right. Yeah, this is a little bit on that. Things I'm not really going to have a lot to talk about, and yeah, happy to talk after. So you could write things in the C kind of look. If functions or modules, what does it mean to have like if some condition? If my switch is 1, then my module. What does that mean? Well, it derives a clock enable, and that's pretty neat. You can insert raw Vhdl if you have existing IP. You can derive clocks, set false tasks, and I mentioned you can say these wires are async, don't touch them, things like that. Yeah, if you've been paying attention, these functions are pure. They have inputs and they have outputs. So data is always flowing from the input to the output. But in a digital circuit, there's oftentimes where you want to go back the other way and have a signal kind of maybe asserting flow control or trying to do combinatorial loops or stuff like that. You can do. Yes, this shared arbitrary FSM. Just to maybe more of a teaser than an explanation. When you have these state machines, and I mentioned you have function call kind of semantics that bring you into sub-state machines. If you have multiple main functions, top level instances of these, it's sort of like having threads, 2 parallel threads going on. And a lot of what's talked about in the arbitration is like, I'm going to declare something else outside of those 2 threads, and I'm going to wire it together with these global wires and stuff, and then put some logic around it so that only one FSM can get into that region, do things at a time, and then come back. And you get kind of a atomic, I don't know, mutual exclusion kind of feel to FSMs. That's pretty neat. And did some kind of wild work where you end up shooting information on like this FSM. You just went into an FSM called like open a file. Well, what does that mean on an FPGA? It doesn't mean anything. But what you can have that FSM do is like send a packet over the network to an actual system that opens a file and like brings the data back to you. And now it looks like your FPGA can like open files on an operating system. So that's fun. And then, so I mentioned sort of abusing the static keyword in C here for, it actually works, the static local variable maintains state, that's great. But volatile here gets used for all kinds of weird stuff where it's just kind of like, this is not going to behave how you think. And there's some interesting features there. And then finally, I'm doing a lot of generating C code to help along. Like you write this hardware description in C, and it's going to be on some system, say, sending some packets to an actual CPU with software. You can generate some C code for the software side to help move data back and forth a little bit easier. And finally here, down at the bottom here, a snippet of GitHub just saying, there's a few bugs out there, and I'm always looking for enhancements. So like that very first bullet point, like what is if a condition like my module mean? Like that's something you get newcomers to HDL doing all the time. They're doing like an always process, and then they try to instantiate a module in the always block, like under some condition. Well, that actually, like you can implement that in PipelineC, like that kind of question of like, well, I wrote this code, what does that actually imply to hardware? That's one of my favorite things to think about. And so a lot of those enhancement ideas are just like yeah, make it so I could just write this in C, and then it does fancy hardware thing under the hood. So that's fun to think about. All right, getting into the example project here, and we're really excited to show you guys this. It's the most complex hardware demo I've ever seen done in PipelineC, and CIRCT here is the first public announcement of it. All thanks to great work by my friend Victor here. And just to go into details, he wrote a ray traced game for PipelineC, but even better, it compiles as C++ and runs as in real time on PC, so you can do your development in real time. To do this, he wrote a C++ parser and generator that lets you generate more basic C syntax, but it gives you all sorts of great things with fixed point. You can do vector math with nicely overloaded operators and things like that. Made the code a lot more clear. It was really a pleasure. We found a lot of bugs and made a lot of optimizations together. Probably close to a year of work on this. So thanks, Victor, for sure. And the specifics of the ray tracer and parser should really be a talk of its own. I'm not going to go into as much detail as there actually is. I'm sure Victor would be happy to take questions. I don't know if Victor is on the call today, I believe, and I don't know if he had anything he wants to touch on before we show the demo here. Give Victor a second if he wants to say something.
Yes, I'm interested in doing some hardware design using FPGAs, but since I'm from a software development background, I always saw that to learn hardware description languages is a bit hard, and I prefer to start with something simpler. So I discovered the tool from Julian, PipelineC. I liked it very much since it's open source and targets many chips. So we started talking about it. And since I discovered that the tool was quite powerful, I thought that maybe the project that could be done with that are more like usual. I saw that most operations that you do with a CPU is in the basics some intercept operation. So if we can write algorithms doing some integral logics, we can do anything, like for example, floating points, fixed points, and anything that you want. So from the start, I wanted to, when you design and test an algorithm, to be able to run it on a PC with a regular compiler, so you can tweak it and make it better and do lots of tests before going to synthesizing it. That takes a lot of time. So we started to interact with Julian. I, in a sense, pushed him to make all the syntax of PipelineC compatible with C, that there is the opportunity to have always a way to write the same algorithm with the same syntax as run on PC and translate well to Vhdl or Vhdl with the same source. So we started to work on that. I selected to do a ray tracer because for a good ray tracer, it's good to have some vector match that is convenient to write with some simple syntax. And I thought that if we do a ray tracer, it will be good to show to other people how far you can go with PipelineC. So we did that project. Since I'm familiar with C++ syntax, I prefer it in some cases. Currently, the parser of PipelineC only handles C syntax. So I decided to write a parser that is based on the C-lang indexer libraries. Unfortunately, the CLang library for doing indexing of the C++ source is not meant for translation. It is designed just to find some symbols in source code, but the library has an interesting property that when you find a symbol, it points where the symbol is defined, so you can have a short string of the source code with the piece of code that represents what is done there. So to get to file syntax of the C++, I needed to parse short strings of C++ that was quite easier. So in the end, I was able to parse most C++ to detect where constructors are, where there are operator overloading and the like. And I was able to write a tool that converts a source writing in C++ to a kind of dialect of C that is able to be compiled with a regular compiler and also with PipelineC. So it was easy to start writing the right tracer, always first compiling it and testing it with a regular compiler, and that way it was easy to develop it and debug it. And well, it required quite a lot of optimization since resources on the FPGA are not a lot. I had to do something to count how many, for example, multiply operations are you using, so not to surpass the available resources of the FPGA. And well, doing that, in the end, we were able to write the right tracer. And once we did it, I thought that it won't be too difficult to add some interactivity to the right tracer. So the offsets that you are seeing in the screen start moving in the way that you like. And well, doing all that, we ended with that project. Well, I hope Julian can show a demo now, and we can continue talking about it.
All right, excellent. Yeah, exactly, demo time. Yeah, here we go, started playing. So here is my lovely fiance playing, and I'm filming here. Notice the delightfully reflective sphere and floor there, and interactivity. Clicking the button there, bouncing around. Yeah, I'll play it one more time just to take a view there. You know, from what I gather, Victor is a lot better at this game than me. I can only get, you know, tens of seconds further and then I fall through the floor. But apparently there's some special features at the end if you're really good at it. Right, so what were you seeing there? This code is available on GitHub. The link there, PipelineC graphics repo. This is Sphere versus Shapes. Sphere bouncing around there. It's a real-time ray trace bouncing ball game. There's no frame buffer. It's all chasing the beam, so to speak. It's 1080p, 60 frames per second, 24 bits per pixel color. And again, it's all auto pipeline. And this is for a 148 megahertz, 148.5 megahertz pixel clock. And again, there's no CPU involved here for any of this animation or rendering that you're seeing. It's all this easy C debug, all from software through FPGA. So talking about this specific demo, what does the code look like? Well, there's two main clock domains for what's going on here. Two main pragma mained functions with top level IO. You have the one frame logic on the left there. It's got inputs from buttons, the human pressing the button, and it's running super slow, 60 hertz. That per frame. This is things animating the frame changes each frame. It's not at pixel clock, so it's a very slow state machine. And on the right side there, the other main function is the pixel logic stuff occurring at pixel clock. It's generating VGA timing. It's generating the frame clock, and it's got a long pixel rendering pipeline in there as well. And its top level outputs are VGA signals. And yeah, so these two wires, these lines here connecting these blobs are those wires that I was talking about. There's a global game state defined wire that gets wired out from the logic doing frame stuff out into the pixels, and the pixel logic is producing the frame clock. Right, so we're gonna go into this a little bit more. So that frame logic that's driving the animation, how does that work? Well, it's also super simple. It's your classic state machine with a current state and a next state. And so you do a little function to determine the next state, and that function takes the form of, give me a state, given the current state, and if the button's being pressed. And you do some logic and see, if the button's pressed and the sphere's touching the floor, then you do this. Again, it's a very slow state machine. You specified to the tool that you have this clock, it's 60 hertz, and it knows that none of this needs pipelining because it's at 60 hertz. And what do we got here? Yeah, I think the final point I wanted to get at here was I don't know if HLS tools can you just give like an arbitrarily slow clock domain and a blob of combinatorial logic described in HLS right alongside something else in another clock domain doing digital logic at hundreds of megahertz. I don't know. And yeah, the final line there, that this the state here from this very slow state machine is being globally wired, written out to be used later, and you'll see that wire coming in. Right. So here I wanted to actually show the actual pixel logic code, that blob that was on the right. This is the actual code right from the file. Hopefully simple to read here. Data flows from your inputs to your outputs, so top to bottom in the function here. You have a module that's generating the VGA timing. From those VGA signals, you send it into another block that uses those to generate the frame clock, so that there's a rising edge per frame as the VGA signals go by. Then you have the long pixel rendering pipeline. It takes what pixel XY you want to render, and it gives you the color. And the final bit there at the end is a connection to the outputs. And if you look down here in the bottom right in green, the global wires aren't shown, and I think that's a good thing. So in this last function call here, pmod registers outputs, you don't see the wires of going out to the pmod connection. That's all handled in some pmod module you pound included, and now you just call this function, and through global wiring that you don't see, your arguments to that function are actually going out and wired to top level IO and stuff like that. So sort of hiding those connections through various hierarchy points and modularizing that way, I think it looks really nice at times. Yeah, the final thing to note here is the blob of registers down the middle here. So you'll notice that the outputs here use the VGA signals. I think it's specifically the active, and there's an H-sync and V-sync in there. And those get delayed along for however long the pixel rendering pipeline is. And so you can just naturally write code using these values, and everything's kept aligned and behaves how you expect. Right, so that's the whole pixel logic code, and there's one more level of going down into this. We're going to talk about actually rendering the pixel there. But before we get into that, a bit of details for going on there. As I mentioned, and Victor got to mention, there's a level of code generation here that lets you actually write C++ with great classes and operator overloading, stuff that C doesn't have, and excellent work by Victor there. I don't know if we touched on it. Yeah, there's a bit of that C-Flex HDL that generates Silas too. That's fun. But yeah, so that layer of code generation is great. The fixed point is handled there as a C++ class structs essentially there. But we also use floating point for some of this math, and that's actually built into PipelineC. There's a series of types called the float EMT types. And that lets you specify floating point types with arbitrary size, exponents, and mantissas. So a 32-bit floating point that you're familiar with, the float type from C is actually an alias to the type float 832 or 23. 8 exponent bits and 23 mantissa bits, and that's your classic 32-bit floating point. In our work, we did a lot of tests on how low can we bring that down and maintain graphics quality. If we bump it up, what does that look like? And resources. And we settled on just defining float to be float 814. So now everywhere you see in our code where it's float, the float type, it's a float with an 8-bit exponent and 14-bit mantissa. Again, getting back to all those math optimizations by Victor, many thanks again. All handwritten, all the classics get brought out here. Your fast inverse square root and your fast square root. There's a fast division in there. It really is a whole other talk that Victor should be able to give. But the little snippet of code down there is the classic fast inverse square root from I believe it's the Quake engine, and but ours had to be modified to support these alternate floating point formats. So now your floating point magic square number changes a little bit if you have different exponent and mantissa bits. So we had to account for that, and there's a few levels of macroing kind of things away here. Get to demo, PipelineC builds in. If you want to do a floating point divided by 2, well, that's just actually operations on the exponent. It got built in as the shift operator, which normally isn't defined for actual C. And all this stuff, as Victor said, you can kind of massage this to be compiled by a C compiler, and we definitely did a whole lot of that. But getting into using that code to actually ray trace a pixel, how does that work? So up there at the top left is that state wire from that super slow 60 hertz clock domain coming on over. And that gets in the top right here marked as an async wire. So it's saying, don't try to deserialize at that rate. Don't insert any FIFOs. Don't do any checking of clock crossing or anything like that. Just a wire, and I'll take the consequences of that wire. It's done like that to essentially avoid wiring it in like an input at 148 megahertz. It's not an input that's changing at 148 megahertz. It's super slow, and so you don't want it brought in like X and Y position on the left there, kind of funneling through your pipeline, and as it's needed, you want it brought to wherever in the pipeline it's needed at the time. And so you get into what is that pipeline? It's a big C function, and it has a function signature that hopefully is understandable. It outputs a color pixel for a given XY input. And obviously this isn't the whole code here, but just a snippet of what's going on. You get some great vector mapping in there. Fun doing your dot products and intersecting rays with spheres. But just highlighting there's that wire read of the state coming in. It's not an input to the function. It's just directly wired in. And it's all meant to be hopefully readable C code. And compilable too. So yeah, that gets to this next slide. So how do you debug this thing? Right, so at the C++ level, you can compile C++ and C. There's a lot of different tools available for that. Some of my favorites, like printf, but GDB is also available. And Victor put a lot of effort into making it like even that software code efficient as well. So you can debug 60 frames per second at 1080p, just your C++ code. So, doing the game, designing the game doesn't have to wait, produce a bit stream or run a simulation or anything like that. It's instant. The next level that we were using is Vhdl, which is a Verilog C++ simulator layer going on there. Very nice tool. We get at it through passing the Vhdl from PipelineC through GHDL. Plug in for Yosis. Yosis spits out Verilog, and the Verilog is what actually Vhdl takes. And that that's all nicely command line argument for you. You can just kick that off. We were just looking at the output signals. I understand from Vhdl you can kind of poke in and get a lot of detail on the inside of the design, but we were just looking at the top level VGA output, kind of printfing bad pixels as they came across. And that you get about 10 seconds to render a frame there. A little bit longer 1080p, but still reasonable. But then the VHDL, you can also send that right into model sim, -s sim --s model sim there. It'll kick that off. And the VHDL is great. There's comments. I think it's human readable compared to a lot of other generated code I've seen. Names are directly derived from your code. And printf actually ends up working. You was able to wire that like through a process to actually writing to the console and model sim. So you can do a little of your favorite printf debugging even in model sim too. And there you get a blazing about a pixel per second in simulations there. And finally, because these the names in the VHDL are derived from the code, you can just do a pragma mark debug, something you've declared as a static local variable, a register, and it'll actually do the VHDL mark debug and make it a little bit easier for when you fire up Vhdl and enter the gateway to FPGA hell with chip scope there. Right. A final fun thing, kind of bring this all together. I mentioned you could use GDB. One of the best experience I had was having the C code compiled with GDB running, and I'm stepping through breakpoints, but then I'm also stepping through the model sim simulation with all the VHDL names based on C code names, and I'm stepping through model sim clock by clock at the same time and just like comparing values. That was a good debug experience there. And then the last note there is, most of our work, most things didn't make it past Verilator. We would show up in Verilator and we'd be able to figure out what was going on. And anything we did end up finding, we were able to recreate. We didn't have any like weird, bad clock crossings or, it didn't meet timing or stuff like that. The tool's checking those things for you. All right. Yes, the hardware results of this thing. So we put a lot of work into optimizing this, trying to squeeze it in here, and it did end up fitting nicely in the larger 100T already here. But there's options we have to scale it down if you want to try it on a smaller device. But to talk about the results, I mentioned this is 148.5 megahertz pixel clock with that big pixel rendering pipeline, and that ends up taking 482 pipeline stages. Why does it have any stages? Well, things like the floating point less than greater than 4 stages, multiplying 6, add an 8. You get down into computing a whole, ray intersecting a plane or ray intersecting a sphere into hundreds of stages. But the tool is, keeping all that aligned for you. You're not having any of those pipeline retiming errors that I so dreaded at the start of this. It's configuring. It's using GSPs in the hardware, configured with their input and pipeline and output registers as you need. And down there, is the utilization. We got like 2/3 of the LUTs. I think what do we got? 2/3 of the LUTs, half of the DSPs, maybe like 2/3 of the registers. And it does indeed meet timing, as you would hope. And I want to emphasize here the kind of little blobs here saying portable. This doesn't need to run on Xilinx Vivado for Xilinx chips. You can use Intel chips and Quartus, Lattice, and Diamond. It also supports using that flow through GHDL and Yosis, but then using NextPNR for the back end there. Had some experiments with the Phoenix tools as well, and some fun ASIC timing models you can use and experiment with. As I mentioned, you can do all kinds of simulation. That said, what was that all about that you just saw? Just a quick summary, some links here. Victor's great repo there with the code generation and the main repo for the graphics there. I hope you enjoyed the cool graphics and your shiny spheres, and that it was all easy C code to debug. Doing the simulations and development in real time, not having to wait for your simulation or even your bit stream to go at doing some testing and development. We wrote the code, so the state and the game state and the logic for moving spheres around and stuff like that is abstracted and isolated away from the part that's rendering the pixel. So you go in and try making your own game if you want. It's reusable code. And to that extent, it's portable in quotes, you might say, in that it'll work on any FPGA device. The auto pipelining isn't specific to any manufacturer. And can you say, is this the first ray trace game that is not any software, no CPU, no instructions going on? I think that's pretty cool. All right. On to talking about CIRCT. But now, yes, now is the scheduled time for questions here. Just I wanted to leave you with saying, for software folks, I want you to write PipelineC and feel like, some subset of C that you're solving a puzzle in, but what's really going on is, the hardware concepts being implied there or hidden from you. But for hardware folks, I want PipelineC to be a better hardware description language. You can write PipelineC that looks a lot like regular hardware description language. You don't need to use the auto pipelining if you don't want to, but it's trying to be there to just, be a better middle ground between RTL and HLS. So I mentioned earlier, we are lucky today to have Victor in the meeting. So if you actually have like in-depth questions about how ray tracer math and stuff is going on, I'm certain Victor would be happy to answer, and I'm happy to take any questions too before talking about CIRCT. Right now.
So on the software side, what are you doing to correct for the different clocks on your different regions?
Yeah, so this isn't meant to be the entire description is compilable with a C compiler and is a clock cycle kind of accurate simulation of the hardware. It's more that the two chunks of code there, the frame logic, animation stuff, and the rendering the pixel, those are two C functions you can pretty much easily split off into their own little test bench and kind of wire together in your own simulation, if you would, or model. But it's not like a clock cycle accurate, anything like an actual simulation you might be thinking of the whole C code design.
So I'm responsible for making sure those execute at the appropriate rates in some outside wrapper for doing a software compile.
Yes, that's right. So our I think the closest thing for us here is like our Verilator simulation, or no, not Verilator. I'm sorry. Our raw C compile simulation, if you will, isn't a cycle accurate thing. It's a loop where each loop we're looping over, all the pixels and calling that render pixel function. And at the end of the frame, we call the update get next state frame thing. It's not a full simulation of the system, but it's kind of like bricked together enough to mimic what you'd expect it to be doing. Yeah, great question. Yeah.
And so I think I missed this at the beginning. You're effectively taking, you're effectively have your own kind of C-level-ish parser.
Yeah, and we can getting on to like how does this get into CIRCT and like all the actual compiler infrastructure. There's some nasty bits. Yeah.
Right. I was just curious because like there's many places you could intercept kind of on just the classic LLVM side to. So I was just curious kind of why you chose like at the parser level.
Yeah, and I think I'll flip to the next slide here because it does get into that. A really easy answer might be I didn't know what I was doing, but in truth, yeah, I don't have a formal compiler education, and so yeah, I kind of, like I said, this is 2014. I'm Googling around for how do you parse C code, and kind of just went from there with the first C parser that I found, and that was nicely in Python. And it's a long story from there, but touching on I think some of the things you were getting at here. Right, if this is relating to actual compiler infrastructure like CIRCT, where do you even begin? Because this is C, so it's really easy to get caught up in things meant to eventually get to instructions on a like CPU with a fixed architecture. And you can do those kind of things. Leg up HLS, I believe, uses MIPS. It'll compile code to MIPS, and it's looking for like hotspots in the execution of the MIPS instructions. And that's one angle. What would it mean to use like LLVM IR as a step in this? Getting at but my general goal is I would like to use shared infrastructure and not maintain all this Python code myself. So what is this code doing, and what might I hope some other infrastructure be able to help me with? I was never able to settle on what exact percentage of PipelineC these bullet points represent. So it's some tens of percent is just the C syntax part. I'm using an unmodified C parser. So I haven't added any like keywords to the language or anything like that, because that's also kind of against my goal of being able to compile it too, because I also don't know how to write a C compiler. So if I'm introducing new language features, I want to be able to compile them and do the testing and fast simulation stuff that we were doing, and I don't know how to do that either. So stuck with plain C syntax for now. And a lot of the work is tracking essentially that bottom chunk of the slide picture there. I have a C function. It has local variables. It has stuff like that derives muxes and operations that, based on the data flow, end up occurring in parallel. So you get this directed acyclical graph, and it's this like data flow netlist kind of thing. So I don't know what kind of front end languages are built for coming from a C syntax kind of area to get to a data flow intermediate single assignment per variable kind of look. And then there's the whole second aspect, which I think is tightly coupled to it here. Then how do you schedule the pipelines there? So like I said, PipelineC knows that, for instance, that floating point adds take longer than the multiplier, and it knows the combinatorial delay for both of those, and it's using that to figure out where it needs to stick its registers. But yeah, all of that's just custom code and a lot of combinatorial logic Tetris bets in there. Yeah, like I said, it's tightly coupled with the data flow netlist kind of representation, and right. And then critical, as you're adding these pipeline stages into these modules and you're kind of rebuilding it, you got to keep the latencies of everything aligned, like that select signal delayed appropriately for the mux at the end there. So yeah, two big chunks of what PipelineC is doing is those two things. And maybe I'll quick go through the last few percent here.
Sorry, just Luis, you had a question?
Oh yeah, another question.
Yeah, so my question was, I imagine that your kind of like canonical scenario where someone writes PipelineC and then just gets the netlist or whatever, doesn't really look too much into the generated Vhdl, Verilog, whatever. But would you consider, is it reasonable to support some kind of scenario where this would just be used to prototype something rough and then look at what the Verilog implementation looks like and kind of get something more human readable on that front, so that maybe you could even be an expert system Verilog programmer, designer, whatever, but maybe you just can't be bothered sometimes and just want to prototype something quickly, something like PipelineC. But then I imagine that if what you get is really kind of like machine readable but not really human readable, then that flow for, oh, I see, maybe this is a good starting point, I'll do the final changes on the Verilog code. That maybe that wouldn't be particularly feasible if it looks too much like machine generated Verilog. Have you considered flows like that and things to improve the intermediate output?
Yeah, so where the generated code becomes particularly ugly is when you get into the auto pipelining, whether, that example, 400 something pipeline stages, that's a pretty ugly looking file. But generally, if you're writing stuff that's not being auto pipelined and just kind of like mimicking what you would do in HDL, I think the produced VHDL is actually pretty readable. I mentioned the names come from the C code. So if you have a static local variable, a register, name with some name, you have a signal in the VHDL with that exact name, nothing else appended to it. It's the register, and you can, I mentioned you can mark debug that and chip scope it and stuff like that. So if you're not doing a lot of fancy auto pipelining, I think the generated code is pretty good. And from that perspective, I think you could go in there by hand and start fiddling around and modifying things by hand if you're an expert. But I think also kind of in that direction, I mentioned you can include raw VHDL. So if you have a module where it's like really, this is best expressed in VHDL, you give it a wrapper C function definition, and then you can just drop in the VHDL inside, and that ends up being what's used there. So there are a few routes if you are an expert and want to mess around with the HDL. But yeah, that's kind of the state of things now. Hopefully that answers your question.
Thanks.
Yeah, no problem. Yeah, and that, happy to take more questions, but perhaps as y'all are thinking, feel free to interrupt me. I'll just talk through these last three bullet points here. Another chunk of the code is actually rendering the hardware description language. Like I said, it's VHDL, and it's the ugly, bunch of printfs of VHDL like everywhere kind of deal. So, all of CIRCT's nice ideas for producing nicely formatted Verilog code. It sounds like a nice dream for me to get access to. And generating the HDL includes specifically pipeline primitives. So if I have a 64-bit adder, but I need to split that into 2 cycles, how can I render, 2 32-bit adder cycles with a carry and have a notion of now this module has a 2-cycle latency kind of deal and be able to work with that. A lot of custom just net list things for VHDL, connecting things together, and all sorts of arbitrary stuff inside that. There's a fair amount of internal C code. So the floating point operators for all those, the various mantissa sizes and configurations, it's just generated C code internally, and then I'm, using that. I don't know if bootstrapping is the actual term there, but the floating point operators are written in PipelineC. So there's, floating point add is you get your mantissa and you shift it around and you add it to this other. There's an actual C function, where you're doing a shift operator and compares, and it's just all more C code all the way down. Another chunk is the actual running of the place and route tools, and synthesis is in there too, to get the delay measurement. So when I talk about I know a floating point adder is longer than a floating point multiplier, well, how do I know that? Well, at some point, it was synthesized and the timing was recorded on it. And another chunk of the code for, even if I go through all this and I try to schedule my pipelines right and put my registers where I think they need to go, it still doesn't meet timing all the time on the first go. So there's a step of iteration, where do I add more registers, or what's the change I actually need to make to meet timing then? And hooks for running all the simulation tools, like I mentioned, the derived state machines and all the fancy arbitrations, another chunk there, and finally generating the helper software C code that a user could run on a CPU to interact with PipelineC designs is another chunk there. And yes, I believe, we are at the end here. So again, time for more questions if you have them. If you just have comments, happy to hear them. We can follow some of those links and actually dive into code. Some Twitter handles there. Find me on Discord. All the good stuff. So again, thank you all, and happy to take more questions. Thank you. Thank you.
I second that.
Can I add something?
Yeah, go for it. Yeah.
Well, can I add something?
Yes, please.
Yes, I think, for example, another interesting project that can be done with that tool is software-defined radio, for example. There are many DSP algorithms for processing signals that are written in C. So with this kind of tool, for example, you can reuse the modules. You can test it with a regular compiler that they are already tested, start plugging in each other. And so we might start implementing, for example, Wi-Fi processing or some advanced software-defined radio that if you don't have vector types, floating point types, fixed point types easily to use, and existing code ready to reuse, it will be much more difficult if you use standard HDL. So with that tool that use C code and C++ code, it will be easy to do that kind of application that are maybe a bit complex with the existing tools. That's one of the aims of the project, and other of the aims, at least for me, is to start gathering more software people doing hardware design. So if you present them more known language and some existing algorithms, maybe they get more interested. So that are some of the next steps for the project.
Yeah, that's great. Yeah, lots of opportunities for future work here. Very exciting.
So unfortunately, I need to drop. Otherwise, I would ask how you envision dealing with kind of non-standalone deployment, where you have FPGAs in the host and you have far more complex stacks to actually talk to them.
Yeah, that's a delightful. That's kind of the whole like accelerator design, the dual like software side design integrated with the hardware side. If I understand where you're getting at, and yeah, that's a huge thing. And, right now, there's nothing PipelineC does other than some light code generation to help you shuffle around buffers. But yeah, that's a huge world out there.
So I'm sorry, I have to drop, but you all are welcome to keep talking. The meeting should keep going without me just fine. Right. But thank you, Julian and Victor, for coming. That was very interesting.
Absolutely, my pleasure. Yeah, I'll be here for just a moment. Like, I have a little bit more time if folks do have more questions. If I didn't get to catch who was asking about the arbitration earlier, but if you're still around and wanted to chat, I'm all for it.
That was me. You and I, Julian, actually chat frequently on Discord. So I'd like to set up, like, we haven't spoken face to face, and you've been encouraging me to try PipelineC, and I'm now bought in, maybe like wholesale. So we should chat.
Oh, great. Yeah. Well, how fun. Yeah. Happy to explore all the features that you find useful.
Hope everybody likes my icon avatar.
Yeah, so I see a few things in the chat here. I don't know if they ended up being brought up or not. I'll try to.
We're probably going to move it to the Discord about the Python bindings. So.
All right. Right now. All right. It sounds like got all the questions from you guys. Thank you very much for having me back again, for your patient attention, and thank you again, Victor, for all your hard work and being here today as well.
Yes, thank you for that, for inviting me and giving me the opportunity to show my work.
Absolutely. Well, all right, folks. I'm going to be heading out. Thank you all for your attention and questions.
Thanks, guys.
Bye.
Bye.